Hello friends, good morning to all of you. I am Nagendra Kumar Moria, Assistant Professor in Department of Mechanical Engineering, GL Bajaj Institute of Technology and Management. In previous class, I have discussed about the detailed design procedure of piston and some numerical problem was also discussed in my second video lecture. In current today class, I will discuss about the force analysis of the connecting rod, and also I will discuss in beginning some brief introductions about the connecting rod. Then I will continue my connecting rod. What is connecting rod? The connecting rod is an intermediate member between the piston and the crankshaft. The primary function of the connecting rod is to transmit the push or pull from the piston pin to the crank pin and convert the translatory motion of the translatory or reciprocating motion of the piston into rotary motion of the crank. It consists of a long shank, a small end, and a big end. The cross section of shank may be rectangular, circular, tubular, I section, or S section. Mostly, circular section is used for the low speed engine, and I section is preferred for the high speed engine. Cross section details of the connecting rod. Here you can see the details of the various cross section in detail. You can see here it is the big end of the connecting rod and it is the small end of the connecting rod. Small end of the connecting rod is basically connected to the piston pin or gudgeon pin, and big end is connected with the crank pin or connected with crankshaft. Here the cross section shown in this figure are in I shape. Mostly I shape connecting rod is preferred for the high speed engine because the moment of inertia of I section is very high. Normally the I section, small end is made in form of I section, and big end is split into two halves because it will help in mounting of the big end with a crank pin bearing. And here is a spout provision for the lubrication of big end bearing, and two half of the connecting rod is connected with the help of bolt. Here the H is the dimension at the middle section of the connecting rod, and H1 and H2 cross section are near the big end and small end respectively. The size of the connecting rod is gradually increasing from H2 to H1. So you can see the proportion of H1 is equal to 1.1 H to 1.25 H at the big end side, and H2 is equal to 0.75 H to 0.9 H. So while calculation we are calculating the value of H, and on the basis of H we can easily evaluate the value of H1 and H2. Note: some important aspects should be take care while designing the connecting rod. The length of connecting rod L depend upon the L by R ratio, where R is the radius of the crank. It may be noted that the smaller length will decrease the ratio of L by R ratio, which increase the angularity of the connecting rod. It increase the side thrust of the piston pin against the cylinder liner. It can be easily visualized in force analysis portion. Later I will discuss in detail why the angularity increases. And larger length of the connecting rod will increase the L by R ratio, This decreases the angularity of connecting rod and thus decrease the side thrust and resulting wear of the cylinder. The larger length of the connecting rod increases the overall height of the engine. Hence, a comparison is made between the ratio L by R, generally kept in about 4 to 5. Material for the connecting rod. The small end of the connecting rod is usually made in the form of eye and is provided with a bush or phosphorus bronze. The big end of the connecting rod is usually made in split in two halves so that it can be mounted easily in the crank pin bearing cell. The split cap is fastened into the big end with two bolts, as I have already shown in the previous figure. The bearing cell of the big end are made of steel, brass or bronze with a thin lining about 0.75 mm of white metal or bimetal metal. The connecting rod are usually manufactured by drop forging process. The material mostly used for the connecting rod varies from the mild carbon steel to the alloy steel. The mild carbon steel or plain carbon steel was used in the range of 2.35 to 0.45% of the carbon. The carbon steel having 0.35% carbon it has ultimate tensile strength about the 650 megapascal, and for 0.45% carbon it has ultimate tensile strength about the 750 megapascal. These steels are normally used for the commercial application in the connecting rod or industrial application. The alloy steel having ultimate tensile strength about 1050 megapascal are used in the aerospace engine or automobile engine. The next topic I will discuss is the lubrication of bearing of connecting rod. The bearing at the two ends of the connecting rod either splash lubricated or pressure lubricated. I have already shown the provision how the splash lubrication is done in the bearing. The big end of the bearing is usually splash lubricated while the small end bearing is pressure lubricated. In splash lubrication system, the cap at the big end is provided with a dipper or spout and set an angle in such a way that when the connecting rod moves downward, the spout will dip into the lubricating oil containing in the sump. We know that in IC engine, in sump lubricating oil is always present, which will cool the lubricate the piston liner also. The oil is forced up the spout and then to the big end bearing. When the connecting rod moves upwards, a splash of oil is produced by the spout. This splash of lubricant finds its way into the small end bearing through the widely chamfered hole provided on the upper surface of the small end. In the pressure lubrication system, the lubricating oil is fed under the pressure to the big end bearing through the hole drilled in crankshaft. The crank waves and crank pin from the big end bearing. Forces acting on the connecting rod. The various forces acting on the connecting rod are as follows. Number 1, force on the piston due to the gas pressure and inertia of the reciprocating part. Second is the force due to inertia of connecting rod, and third is the force due to friction of the piston ring and of the piston, and fourth one is the force due to the friction of the piston pin bearing and crank pin bearing. Force on the piston due to gas pressure and inertia of reciprocating parts. Here in this diagram you can easily visualize how the forces are acting inside the connecting rod. Here is a piston pin, and this is the piston. When the fuel is in combustion chamber, when fuel is burned, the gas will apply a pressure on the head of the piston. That force is Fp, and Fn is the reaction of the side thrust force, and Fc is the forces in connecting rod, where R is the radius of crankshaft, and theta is the angularity. As you know, when Fc theta is increases, then the component of Fn will also increase. This is the line diagram of the forces Fp, Fn and Fc. The root cause of the force Fn and Fc are Fp applied due to the gas pressure. Let us assume P, small p is the maximum gas pressure, T is the diameter of the piston, A is the cross-sectional area of the piston. The cross-sectional area of the piston are in circular, that's why its area is pi by 4 d square. Mr is the mass of the reciprocating part. The mass added in the reciprocating part is mass of the piston and gudgeon pin, etc., plus 1/3 mass of the connecting rod, because the mass of connecting rod is assumed to be concentrated 1/3 at the piston pin, and 2/3 of the mass is concentrated at the crank pin bearing. So 1/3 of the mass of connecting rod is added with the mass of the piston while solving. Omega is the angular speed of the crank, phi is the angle of inclination of connecting rod with the line of stroke, and theta is the angle of inclination of crank from the top dead center. Capital R is the radius of the crank, and small l is the length of the connecting rod, and n is the ratio of L by R. The N by R ratio already you have studied in theory of machine chapter, force analysis. The forces on the piston due to gas pressure will be Fl, that will be equal to the pressure multiplied by area. Here pressure is P and A is the pi by 4 d square. And inertia force of the connecting rod Fi is equal to mass into acceleration. Mr is equal to Fi is equal to Mr into R omega square bracket में cos theta plus cos 2 theta by L. And I am not writing the expression how it come from, because it is already discussed in your theory of machine chapter, where it is important for the derivation aspects. Here only numerical aspects are required, so that's why I am directly using this relation. The inertia force of reciprocating parts oppose the force of piston when it moves during the downward stroke, because inertia force always support the causes of motion. Oppose the causes of motion. On the other hand, the inertia force of the reciprocating part helps the force on piston when it moves from the bottom dead center to top dead center. Equivalent net force on the piston pin, that will be equal to the force due to gas pressure plus minus plus inertia force, that is equal to Fl minus plus Fi, where when negative sign is used when the piston moves from the TDC to BDC, where here TD stands for the top dead center and BDC stands for the bottom dead center, and positive sign is used when the piston moves from the bottom dead center to the top dead center. When weight of the reciprocating part is to be taken into consideration, then Fp is equal to Fl minus plus Fi plus minus Wr, because weight is occurred due to the gravity, and it acts downward. Always downward direction is taken into positive and upward direction is taken into negative. That's why the sign convention for the weight is plus minus Wr. And forces on the connecting rod can be easily calculated once by using this diagram. Here we have already discussed how the force Fp is calculated in the previous slide. So by using this relation we can easily identify the value of Fc and Fr. The value of Fc in terms of phi can be calculated. Fc is equal to Fb by cos phi, and which can be calculated Fp divided by, we know that cos phi is equal to under root of 1 minus sin square theta by n square. This expression basically come in from the theory of machine force analysis chapter. I have directly using this relation. The forces in connecting rod will be maximum when the crank and the connecting rod are perpendicular to each other. But at this position, the gas pressure should be decreased considerably. Thus, for all practical purposes, the forces in the connecting rod Fc is taken equal to the maximum force and the piston due to the gas pressure, and neglecting the piston inertia effect. Force due to the inertia of connecting rod. Inertia force is calculated by using the following relation: m r omega square divided by 2. I am not writing about the detail how this expression come from. I am just writing the expression used for the calculation of the inertia force. This resultant inertia force act at a distance of 2L by 3 from the piston pin. Since it has been assumed that 1/3 of the mass of connecting rod is concentrated at the piston pin and 2/3 at the crank pin, therefore reaction at these two ends will be in the same proportion. Rp is equal to 1/3 of Fi and Rc is equal to 2/3 of the Fi. Here Fi is the inertia. Force is due to the friction of piston ring and of the piston. We know that the friction force that will be equal to the mu into n, where n is the normal force, and that will be equal to the force can be written in terms of normal force in terms of pressure into the perpendicular cross-sectional area. The cross-sectional area can be easily calculated by P, where PR is the pressure of ring and pi d is the perimeter, and perimeter is multiplied with the thickness, axial thickness or axial width of the ring, then it will be converted into the area of one ring. There are n such rings, that's why we have multiplied with n. So we can calculate by using this, you can easily calculate the area of the n ring. The value of pressure is normally used about the 0.025 to 0.04 megapascal, and coefficient of friction mu is taken about 0.1. Since frictional force of the piston ring is usually very small, therefore it may be neglected. The force due to the friction of piston pin bearing and the crank pin bearing. The force this can be calculated sigma c direct compressive stresses plus maximum bending stresses due to the inertia of bending stresses. Normally the value of this force is very less, so it can be easily neglected while solving. The references I have used a book RS Kurmi for the preparing these slides. Thank you very much for watching this video. I will upload some more video related to the detailed design procedure of connecting rod and numerical problem, how to solve some numerical problem for the related to IC design of